Hello, welcome to a new video of Science Video Maker. Here we are going to continue with gravitational field strength. And we initially seen in gravitational field strength that gravitational field strength is a gravitational force per unit mass. From this formula, we can see that the gravitational force, is equal to the mass times the gravitational field strength. And now, we know that by relating the Newton's second law with the Newton's law of gravitation, we are going to have the formula to conclude the formula of gravitational field strength as being as G all over R squared. This is the general formula of the gravitational field strength, which is big G all over R squared. Now, let's see. We've seen that gravitational field strength are going to have different cases. Since gravitational field strength is inverse proportional to R squared, it is going to be considered both at the surface of the Earth, it can be considered above the Earth's surface, and it can be considered inside the Earth's surface. So these are the three main cases of gravitational field strength calculations. We've initially seen in case 1, which is on the Earth's surface. On the surface. Here we see that gravitational field strength on the Earth's surface is equal to G, the mass of the Earth, because the mass of the Earth is the one which is interacting with us, me, you, and everyone, even my pen, on this Earth's surface. So it's the big G, which is acting on, it is the G of the Earth's surface which is acting on all of us. Now, we see here that there is a concluding factor, and here the R that we are using is the RE. The RE is the distance from the center of the Earth, and that is the radius of the Earth, which is being given in this case as 6,400 kilometers, which is a constant. So, a concluding factor is that our gravitation field strength at the Earth's surface is actually a constant, because G is a constant that you know the value, you can find the value and have it. ME is a constant, the mass of the Earth is not changing, except that you can speak about radioactive changes which are taking on the Earth's surface, but this is very minute. The mass of the Earth can be said to be quite constant. And the RE is not also changing. That is why you can have a G at the Earth's surface. And now, the G at the Earth's surface can be given as a value that we already know, and that value will be 9.8 Newton per kilogram. This value is mainly used in when we are moving with mechanics. Every time we want to use mechanics, we are using always this acceleration due to gravity as 9.8, and that's the gravitational field strength at the Earth's surface. That's why I initially said before in our last tutorials that acceleration due to gravity and gravitational field strength are quite the same, but the difference between them is that acceleration due to gravity is a subset of gravitational field strength, because acceleration due to gravity is only one component of gravitational field strength, and that component is on the Earth's surface in case 1. Now, in case 2, above the Earth's surface, let's say that you have an object which is above the Earth's surface. Now, the center has a separation from the surface, which is the radius of the Earth. And the surface has a separation from the object, which is the height. The total separation from the object to the center will be given as the distance d. So G above the earth will be giving us big G, the mass of the earth, all over d squared. This d squared is the total distance of the object from the center of the earth. Now, when substituting the values RE and H inside, I have G above the earth be equals to big G ME all over RE plus H all squared. That's the concluding factor for case 2, and case 2 is above the earth's surface. Now, let's see the third case. In case 3, we consider inside the earth's surface. So, case 3 will be inside the earth's surface. Inside the earth. Now, let's illustrate this. Let's say we have the earth's surface here, the center is here, and now our object is no more above now on the earth's surface, but it is inside the earth's surface. That is, I can decide to dig a hole. I dig a hole or a well in the earth's surface. Why, after digging a well on the earth's surface, I throw a big stone inside that well. Now, my question is that I want to find which force or gravitational field strength of the earth is acting on that big stone that I just threw. Now, the well is what I have already dug, I've constructed. Now, this is my big stone or the object that I want to find the interaction of gravitational field strength due to the earth. Now, the distance between this, the center, to the object will be R. Let's say it's called R. Now, we see from here that we already know our general formula for gravitational field strength as Gm of the earth all over R, be it any type of R squared. Now, in this case, G will be equals to Gm all over R squared. This is G inside the earth. But though I have closed in square brackets, this is not the final formula for gravitational field strength inside the earth. Why? I know that if I dig a hole inside the earth's surface, quite a high distance below the earth, let's say that distance is h below the earth, I realize that the force which will be acting on this big stone that I've just placed inside my wall will not be as a result of the whole earth. The force will be as a result of a certain extracted mass inside the earth's surface, because the earth's surface, the ball or the stone I've just placed inside the wall is no more interacted by the whole mass of the earth inside the earth. So it's only this small portion, extrapolated portion of the earth's surface which is going to interact on my stone. Now, this portion, let's say that portion is called ms. That's an assumption. The portion is going to have a mass ms. Now, so I'll place G inside the earth will be equal to G, the mass ms, all over that R, separation from the center of the earth to the portion where there is my object, R squared. Now, there are certain points to put in our minds here. We know again from Archimedes' principle, if we are going to see in Archimedes' principle right in fluid mechanics later, but now we are not going to speak about that. But I just want to bring us some minds. Basic physics tells us about density. And we know that density is being given as the mass per unit volume. Now, you see that ms here will be equals to a certain density times the volume. Now, I need to ask a question before I proceed. If I take a cup of water and I go to a sea, I take the whole sea. I take just a cup of water and I take the whole sea. Then I decide to calculate both of their densities. The question will be, which density, provided that the constituent of the cup of the water and that of the sea are the same, which density between that of the cup of water and that of the sea will be greater, or how will they differ? The answer to this question is that both of the densities are equal. Density of water remain the same, be it large or small, depending on that the constituents are the same. The density of the water will be the same, provided that the temperature is constant to prevent the expansibility of water. Now, it's the same case here. In this case, the extrapolated mass here, m, is part of the earth. So the density of the whole earth will be equal to the density of this extrapolated mass. So let's come back again. We see that the ms is going to be the density not only of S, but is also equal to the density of the earth's surface times the volume of S. Now, so we conclude by saying ms is equal to the density of earth times the volume of S. Now, we said again initially that anytime that we want to consider the Newtonian law of gravitation, we are always considering circles and not ellipses, as we have seen in Kepler's law. Now, we know that in this case, the Earth's surface is going to be considered as multiple circles, which is going to be a sphere. The volume of a sphere is being given as 4 all over 3 pi radius cube. This is from basic mathematics. Now, we see here that this radius is the distance, r there is the distance from the center to the point where there is my object. So I can substitute back in, I have ms will be equal to my density of the earth all into 4 all over 3 pi radius cube. I can substitute all this again in my initial formula. So my g inside the earth will be equal to g all over r into, I place all this. So I have density of the earth 4 all over 3 pi radius cube. R and here can cancel to give a square. So my g inside the earth will be equal to 4 all over 3 pi g whole of the earth r. Here is a squared, so I'll place a square here and cancel to have an r. So this is my final formula for the g inside the earth. Now, we are going to conclude by saying that we had 3 formulas of g's. In case 1 we've just found above was g on the earth's surface, and g on the earth's surface was being given as g on the earth's surface was equal to g, the mass of the earth, all over r e squared, which was said to be constant of an approximate value of 9.81, depending on if you are on the equator or you are the poles. We are going to see how to distinguish and why there's a change between you found in the equator and the poles. In case 2, we have g above the earth. G above the earth was being given as gme all over re plus h all squared. And in case 3, we are going to have g inside the earth, and g inside the earth is 4 all over 3 pi g density of the earth r. Now, from here, we can conclude that g at the surface is a constant. On the earth's surface is a constant. G above the earth is reducing with the more the distance from the earth's surface increases, because the more h increases, the more the lower values increases, and the more the lower values increase, it makes the whole value to decrease. And here, G inside the earth shows that the more I live from the center of the earth to a point above the earth, above the center, but still inside the earth, the more the G is increasing. So inside the earth, G is directly proportional to R. On the earth's surface, it is a constant, an element of real numbers, and above the earth, it is inversely proportional to R squared. So this is the concluding factor of gravitational field strength. Thanks for your kind attention.